Welcome back, Math 253, Calculus 3, Cañada College. My name is Ray Lapuz. We are now in section 2.5. So we've established some information about vectors in 2 dimensions and in 3 dimensions. We got the dot product and cross products under our belts. Now we're going to find equations of lines and planes in space. First, let's take a look at lines. Equations of lines in space. For you to find an equation of a line, you need 2 things. You need a point and a direction. So if you have a given point x naught, y naught, z naught, and a direction a, b, c, it's essentially going to be the point plus t times the direction. And so what you have here is a parametric representation. Given the parameter t, you have a parametric representation of your equation of a line. In vector form, you can write it as just generically as the point plus t times the direction. But if you take that equation and then you split it up into the x component, the y component, and the z component, you have your parametric form. Now, if you take each of those components and solve for t, then t is going to equal to something with an x, t is going to equal to something with a y, and t is going to equal to something with a z. You set all those x's, y's, and z's, then you get what's called a line in symmetric form. This is one way to eliminate the parameter in 3 dimensions. One thing to note though is that these equations are not unique because your direction vector could be scaled, could be going in the opposite direction. Your point can be any point on the line, and so you have a variety and, well, essentially an infinite number of choices for your points and your directions. So any of these things can look different from each other and still be describing the same line. So just be aware that the representation of your line is not unique. Unlike y equals mx plus b, where if you write it in that form, it's going to be the exact same answer all the time. You won't see this in 3 dimensions. After that, we're going to take a look at the relationship between lines. So either the lines, if the lines have the same or parallel vectors, direction vectors, then they are either equal. So remember that lines might not look like each other, but they might still be the exact same line. So they could be equal. If they're not equal, then they're going to be for sure parallel because your direction vectors are parallel. Now, if your direction vectors are not parallel, they can either intersect at exactly one point, or if they don't intersect and they're not parallel, then there's a possibility for your lines to be what's called skew, which is not parallel and not intersecting. So let's take a quick look at the relationship between lines and how to check. And the idea is to check, first of all, if the direction vectors are parallel. If they're parallel, you can check if they're the same line by just putting in a point on the line. If you take a point on one line and put it in the other and you got the equations to agree, then they're the same line. If you take a point on one line and try to put it in the other line and they're not the same, then you're going to have some sort of inconsistencies in your equations. Now, if they are not parallel, then they might intersect. So we can check if 2 lines intersect by setting the components equal to each other. Now, if they intersect, they might intersect at different times or different parameters t. So when we do this, we tend to set one of the parameter as t, and then we change the other parameter with another letter like s. And then we try to solve, essentially, we're going to have 3 equations and 2 unknowns. And if we get a solution for that, then we can say that the lines intersect. Now, if we don't get a solution for that, then they don't intersect, which means the only other possibility for your line is that they are skew. Now, if the lines are parallel or if they're skew, that is to say, if they're not the exact same line or they don't intersect, then there must be a distance between the 2 lines. And one way to find distance between 2 lines is to find the distance between a point and a line. And one way to find the distance between a point and a line is to establish, if you remember, the magnitude of the cross product gave us the area of the parallelogram. So we can find the distance by finding the magnitude of the cross product and then divide it by v. So what we're doing here is essentially finding the magnitude of the cross product, and then we're dividing out by v. So this is kind of a combination of the cross product and the projection. But this is an interesting formula to use to find the distance between a point and a line. After looking at that, we can take a look at equations of planes. So we're doing lines and planes. And as we start looking at equations of planes, we want to be able to describe a plane given two pieces of information. The two pieces of information that we need are a point on the plane and a normal vector. So why a normal vector? It turns out that if you have a normal vector on the plane and you have a point on the plane, you can find any other generic random point on the plane by creating a vector PQ that's on the plane. And so that vector PQ is on the plane, and then if the normal is indeed perpendicular to the plane, then the dot product of those two vectors must be equal to 0. So we can construct, let's say P was a fixed point, x naught, y naught, z naught, and then you have a normal vector ABC. And then Q was just another random point on the plane. And we can randomize that by just generically calling it x, y, z, as in the variable x, y, and z. So the difference between P and Q is just essentially the difference, the subtraction. So it's x minus x naught, y minus y naught, z minus z naught. And then you dot that with ABC, your normal vector, and then you should get 0. Now, if you have that equation, you actually have all scalars. So this is what's called the scalar form of the equation, or the general form of the equation of the plane. And sometimes we write ax plus by plus cz equal to d, or in this case they kind of have it written backwards, but in any case we can figure out what d is equal to, and d is just going to equal to the dot product. If you look at this carefully, it's really a times x naught, b times y naught, c times z naught, and you're either all adding or all subtracting them. In any case, it's the dot product of the point P and the vector n. That's something to think about. So you can think about that as you're doing some of these problems related to equations of the plane. Now that we've established an equation of a plane, we can find the distance between a point and a plane. And to find the distance between a point and the plane, we're going to rely on projection. What we're going to do is we're going to randomly, well, not randomly, but we're going to find a point on the plane, and you can probably just guess at some points, like fix some x and y value, and then you can find a z value to satisfy the equation of the plane. So you find the point on the plane, and then you make a vector from that random point on the plane to the point that's not on the plane, and then you project that onto the normal vector. So by projecting that onto the normal vector, you're going to get the distance. Now we're going to find another distance formula that's a little bit nicer looking than this, but this is the generic idea of how they came up with that formula for the distance. Now let's take a look at the intersection of two planes. If two planes intersect, they're going to intersect in a line, provided that they're not parallel. And furthermore, the angle between the planes where they intersect is actually exactly the same as the angle between the normal vectors. So if you want to find the angle between two planes, you just find the angle between their two normal vectors by finding the dot product. And then if you want to find the intersection between them, what you can do with these normal vectors is that you can find a vector that's perpendicular to both of them. And if you remember, the way to do that is to get the cross product. You cross n1 and n2, you're going to get the direction of that line of intersection between those two planes. And then all you have to do is find a point that's on that line, which is not an easy task. But if you fix an x value and a y value, and then you put those equations on the plane, and then you can find a z value, then you might have a shot at finding a point on the line. And then finally, let's establish more distances. So we found a distance between a point and a line, we found a distance between a point and a plane, and just as I mentioned earlier, there's actually a nicer formula to find the distance between a point and a plane, and here's that nice formula. Now that we have a distance between a point and a plane, we can find the distance between two parallel planes, because what we can do is keep one plane as a plane and find a point on the other plane, and then now find the distance between the point and the plane. And you can also find the distance between two skew lines, because two skew lines actually lie on parallel planes. And so once you've found those two parallel planes, you can just find the distance between those two planes by finding the distance between a point and a plane. Okay, so a lot of these will take a lot of work to get used to, and practice, just so you can get used to being able to find these things comfortably. All right, that is our overview of section 2.5. Good luck.